Let's look at types of organic reactions. Now, reactions can be grouped into 4 major classes based on the type of the reaction, that is, what kind of reaction is occurring or taking place, and then how the reaction is occurring. So we have 4 types of reactions, or 4 types of basic reactions. We have addition reactions, elimination reactions, substitution reactions, and rearrangement. So the easy way to look at addition reactions is you have this compound here, and then you have HCl. So this reagent adds where the double bond was. So technically the double bond disappears, as you can see in the products. So the H and the Cl add where the double bond was to give this product here. So you can either put the Cl here and the H here, or the H over here and the Cl here. So you've added HCl on the double bond, and the double bond has disappeared. In elimination reactions, this is actually the opposite of addition. So here there is no double bond, but when you eliminate, that means you remove the H and the Cl, and where you remove them from is where the double bond forms. So you can see that in addition reactions, you had a double bond, it disappeared. In elimination reactions, there is no double bond and it appears. In substitution reactions, you have this reactant and that reactant exchanging places. So right here, you have a hydrogen. So one of these Cls replaces the hydrogen. So it goes here to become this product. And then the other Cl joins with the H to form HCl. So technically the H and one Cl have exchanged places. In rearrangement reactions, you can see that you have this compound here. There's a double bond here and 2 methyls. But in the product, the 2 methyls have been separated. So rearrangement reactions occur when a single reactant undergoes a reorganization of bonds and atoms to yield isomeric product. So this compound and this compound are actually isomers. So again, rearrangement, you can tell that these methyls were together, but now they are separate. Let's look at stability of alkenes. You can determine the stability of alkenes by measuring something called heat of hydrogenation. This is the heat that is given off when a compound is reacted with hydrogen. So for example, if you have this compound here, you put in hydrogen, so the 2 hydrogens add on this double bond. So you can see that you've added 1 hydrogen here and 1 hydrogen here. So this is actually an addition reaction. So you see that you had a double bond, the double bond has disappeared. So when you add hydrogen, normally you need a catalyst. There are various catalysts that you can use. You can use palladium on charcoal, you can use platinum, or you can also use nickel. So when you add hydrogen on this double bond to get this alkane, heat is released. So this is actually an exothermic reaction, and you can tell by the negative sign here. So this is called heat of hydrogenation. Hydrogenation because you're adding hydrogen. So you can see that this compound here is trans. So about the carbon-carbon double bond, the methyl is up, this methyl is down. So they're on opposite sides. So this is trans. In this compound here, you can see that the 2 methyls are on the same side. So we say this compound is cis. So when you react a trans with hydrogen to get the alkane, you get 116 kilojoules per mole of heat released. In this case, if you take a cis compound and then you also react it with hydrogen, to get the alkane, you release about 120. So here, the key thing to consider is the more stable alkene gives off less energy. So when we say less energy, we're just looking at the value. Okay, so this is 116, this is 120. You're not looking at it as negative 116. Again, the negative just means that this is heat released which means that the reaction is exothermic. So you're comparing 116 versus 120. So you can see that this compound releases less energy than this one here. And so this trans compound is more stable compared to the cis compound. But you can also tell, that if groups are away from each other, that means they're trans. There is less steric hindrance, and therefore this compound tends to be more stable. Whereas if the methyls are close together, that means there's a lot of steric hindrance here or steric interactions, which makes the compound less stable. So this agrees with what we see based on the heat of hydrogenation. So alkenes can be ranked in order of stability based on heat of hydrogenation. So here you have a table of various alkenes, and if you look at the heat of hydrogenation, again, we are looking at the value and not the negative charge. So when you look at this carbon here and this carbon here, you can see this alkene has 4 substituents on the double bond. So we have 1, 2, 3, and 4 substituent. So we say this alkene is tetra substituted. Tetra for 4 substituents. This one has 1, 2, 3, so this is called a tri-substituted alkene. This one here has 1, 2, and this is trans, so this is a trans di-substituted. 1, 2, so di. This also has 2, but this is a cis, so we call it a cis di-substituted. This has only 1, so this is called a mono-substituted. So based on the heat of hydrogenation, we can see that tetra-substituted are more stable, followed by tri-substituted. And then in the previous slide, we saw that the trans was more stable than the cis. And then finally, the di-substituted are more stable than the mono-substituted. So here, this is more stable, and this is least stable. So what factors contribute to the stability of alkenes? We have 2 factors. One is called hyperconjugation. The other one is bond strength. So what is hyperconjugation? This is the stabilizing interaction between the carbon-carbon double bond and the adjacent CH bond. So this carbon-carbon double bond interacts with the adjacent CH bond, and the presence of this CH bond helps stabilize this carbon-carbon double bond. So if you have more CH3s here, so instead of a hydrogen, if you have a CH3, another CH3 here, another CH3 here, that means you'd have more interactions between this carbon-carbon double bond with adjacent CH3s. So like CH3s like this one, the interaction between this carbon-carbon double bond and the adjacent CH helps stabilize the carbon-carbon double bond. So the more substituents that are present on the double bond, the more hyperconjugation, and therefore the more stable the alkene. And this is why we said tetra-substituted, which would have a CH3 here, CH3 here, CH3 here, and a CH3 here, will be more stable. Another factor that contributes to the stability of alkenes is bond strength. So remember in chapter 1, we talked about a carbon-carbon single bond, carbon-carbon double bond, carbon-carbon triple bond. And we said this one was stronger, followed by this one here, and then this one here, because this one here, the nuclei are further apart, and therefore it is weaker. Whereas in this case, because of the triple bonds, it draws this carbon and that carbon much closer, so that means the nuclei are closer together, and therefore this bond is stronger. So in this case, in terms of bond strength, we are looking at how many sp3, sp2 bonds you have. So if you have an alkene, which is, for example, here di-substituted, so one group here and one group here, versus a mono-substituted alkene, because it only has one group. So please note that here we have a hydrogen and another hydrogen and another hydrogen here. Hydrogens are not considered as substituents. Okay, so in this case here, this bond here is made by an sp3 orbital which bonds to another sp2, and then this bond here is an sp2 with an sp3. So these are the orbitals that are making this bond. So in a di-substituted alkene, we have two sp3 sp2 types of bonds, so one here and another one here. If you have a mono-substituted alkene, you have here, for example, an sp3 sp3 and then an sp2 sp2 sp3 or sp3 sp2. So in any compound, if you have more of this type, that means sp3 sp2, it means that this alkene is going to be more stable. Okay, so therefore the more sp3 sp2 bonds present in an alkene, the more stable the alkene. So hyperconjugation and bond strength are two factors that contribute to the stability of alkenes. So in the next slides, we're going to be looking at polar reactions, and we're going to be looking at how a nucleophile reacts with an electrophile. But before we do that, we need to remember how to be able to identify a nucleophile. So we've already talked about this in previous chapters, in chapter 2, when we're talking about acid-base reactions. But I want to rewrite this again as a reminder. So you can identify a nucleophile by checking whether the given compound has a negative charge, or if it has a lone pair of electrons, or now if it has a multiple bond. So if it has a double bond or a triple bond, then it's going to be considered as a nucleophile. Electrophiles are identified by a positive charge, an empty orbital, so for example in this compound here, or a partial charge. So in class, we're going to go over various polar reactions, and we're going to be able to use curved arrows to be able to show how electrons move between the nucleophile and the electrophile, and then what products are formed.